my name's Steve Smith, and I'm here to talk a bit about Git and really a bit about how it works and why it did that strange thing to you and you couldn't work out how to get out of trouble. Well, hopefully this will help you get out of trouble later. How many people here are from Amsterdam? Cool. I actually used to live in Amsterdam for 2.5 years. I only moved away about nine months ago, which means naturally I speak no Dutch at all. But all I'll tell you about an Amsterdam miracle. I went away about 9 months ago. I came back, and my bike was still there. We were like, shit, no, seriously? That's never happened. So, yeah, if you're not from Amsterdam, lock your bike up. So anyway, so this is about understanding Git. So Git is one of those things that you can work with at a certain level, and you'll be fine. But eventually you'll start hitting the intermediate level problems, and hopefully this will help you solve some of those issues. It comes to a certain point where you need to understand Git rather than just work with Git. And hopefully this will help you out with that stage of your journey. So, not a good time for this thing to working. Have we just lost video? Oh. Oh, cool. Right, we're back. Okay. So you'll probably seen this quote quite a lot. Git is fundamentally a content addressable file system. You may or may not know what that means. Generally speaking, once you've started with Git, you generally don't need to worry too much about that, but eventually it becomes a problem. And there's a reason why you don't actually have to deal or shouldn't really deal with this at the start, because it doesn't really help you in any way, shape, or form. So last year at Git Merge in France, great conference, recommend going to it if you can. Emma Jane Hodgkin-Westby gave a talk about teaching Git, and she made a point that, all this stuff about content addressable file systems, acyclic graphs, it's no use to people who just want to get shit done on a day-to-day basis. They just want to get their code out, they want to check it back in again. And talking to them about this kind of thing does not help in any way, shape, or form. The problem is, once you start using Git after a while, you start learning about branches, merges, rebases, all the rest, you start actually hitting some real problems. And you often end up with something that looks a bit like this. Oh, my clicker has given up. This, by the way, is Git flow. This is a recommended way of managing a Git repository. Don't touch it myself. Can't really recommend it. But people actually think that this is a good idea. The problem is, once you get into this situation, you're going to start hitting weird problems. You're going to think, I can rebase it my way out of this, and it'll blow up, and so on. Unfortunately, at that level, this very novice, naive way of looking at Git as a bunch of commands doesn't work. You need to start thinking about how Git works under the hood. So this is what this talk is about. It's for people who have started to use Git and got into trouble, or trying to work out how they can use it in a more advanced way. So presumably everyone's seen this XKCD. Basically, you'll get into trouble, and then you'll go and find that one person who, what you do is you'll basically blow it away and just recheck it out again. But if you've seen the hidden text in that, there's always that person. I think most people know them. There's one in the company, generally, just one, and they understand Git. And they'll explain to you, blah, 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 this and the other. And eventually they'll give you the set of magic commands. The trick is, that person doesn't actually know that those commands exist. They've merely assumed they have to exist because they know how Git works, and they figure someone else must have written this command to modify the Git tree in some way. So the purpose of this talk is to make you that person, the person who understands Git. I'm not going to tell you a bunch of commands. We'll actually see very, very few of them in this. What I will show you is how to work out what command must exist in Git in order for it to work, and then be able to get yourself out of trouble. So we're going to jump down and let's start right at the bottom. I'm going to take you through the Git internals from the ground up, the fundamental building blocks, and that is how you reason about Git, and that's how you understand how to get yourself out of trouble. And then later on, we will show you how you can apply that knowledge to some common problems and one little weird trick that I can show you, because everyone likes a weird trick nowadays. So, right at the bottom of the stack of Git, in the layers of technology, is the blob. Everything is sooner or later a blob. So, the blob is the fundamental building block of Git, and essentially the only thing you're really doing is manipulating blobs. To give you a little jump forward, this is actually, by the way, the entire Git model right here. If you want a Git model in a slide, that's it. There is basically 3 types of objects. Blobs, which is binaries, trees, which are just blobs that have certain type of information in them, and commits, which are, again, another type of blob that has a certain type of information in it. So I'm going to take you through, from the ground up, how you can work with those. So the first thing we're going to do, we're going to look at this in action at the lowest level. We're going to start with an empty Git repository. So what you have here is Git init, which will create an empty Git repository. And so these are all just Unix shell commands. The tree command, by the way, is just like recursively lists a directory. Now, when you do a git init, it creates a bunch of boilerplate files, in particular a bunch of sample hooks and stuff you don't need to worry about very much. We'll stick to the objects. The objects are what we're interested in, the blobs. And as you can see, there's nothing in there. That's just 2 empty directories, an info directory and a pack directory. So let's add something to the Git tree. We're going to do touch something called Somefile. Touch is just a command in Unix and OS X that will update the timestamp on the file, or if the file doesn't exist, it will create an empty one for you. So that is creating an empty file. Then we'll do a git add. We'll say, Git, we want you to track this. Don't commit it yet. We just want you to keep an eye on this from now on. And let's have a look back at our objects again. So now we can see that there is a single object in the tree. The tree is broken up, so what happens is it's cached. It goes through a process to compress it. It is zlib hashed, and then a keyword header, I think it's 2 bytes, is appended to the front of the file to just mark what type it is. And that is basically it. It's a zlibbed, it has a header put on the front of it, and then it is hashed, SHA-1 hash. Now what this means is, and this is what the talk about content addressable file systems is, the address of it, the hash, is based on the content. If you change 1 bit in that file, the hash changes. It's now a completely different object. This is what content addressable file system is. This is anywhere in the known universe where the same laws of maths apply. If you create an empty file, it will always have that hash, regardless. And that's what content addressable file system means. So it's zlib compressed and hashed. But we're not really tracking it yet properly. We don't have any commits, and we don't have a file name for it. So let's have a look at what happens next. We're going to commit the file. We'll say we want this to be the first commit in this tree. And let's go back and have a look at these again. So, as you can see, we now have 3 objects in here. One is the blob, the original binary, the contents of the file, which is actually nothing. And we have the tree, which points at the object, and the commit, which gives it a place in time. Says this is a bunch of metadata about that. Again, this is the simplest level. This is what a Git repository looks like. You've got the object that contains the content. The tree, we've talked about that for a second, is very similar to a directory in a file system. It contains a bunch of metadata about the file. The content itself is not the file name. The file name is in the tree. It references the hash and it applies additional metadata. What is the file name? What is its permission flags? And so on. Trees can also point at other trees, which gives you a recursive directory structure. This is one of those cases where it's pretty obvious that this was designed and built by a file systems guy, basically Linus Torvalds. But trees change over time. You add content, you remove content, you change file names, and so on. The commit gives you a point in time. By referencing a certain tree, a hash, which is hashed itself, remember, we point at that hash of the tree, we capture recursively the state of that file system at that point of time. And that will remain that way. You add a new commit, you make changes, a new tree will be created, a new commit will point to it, but that old version will still be there. One exception is you can occasionally clean data up, but I will come to that a bit later. But that doesn't really give you anything over time. So the way Git does version control, in a sense we normally talk about it, is version control is what is at its core, is we can chain the commits together. Sorry. It's working? I'm having lots of fun today. So what happens is commits are chained together. Commits can point to other commits. In particular, there's a concept of parent commit. You say, this commit is based on start with the previous commit, and then this is this commit, and gives you changes over time. Fun fact, you can have more than one parent as well, and we'll come to why that's important. So this is really, again, the core of Git. Commits point to trees, trees point to objects and possibly other trees, so you have a recursive structure, and then commits can point to other commits, which gives you a changing system over time. This is the core of Git. Now, an important fact here, it really goes back to some of the earlier days of Git, but if we're going to do something different, do something here now, we're going to echo put some information in that file. So echo just, and the pipe says, add some additional information to the file. So we're adding, it's no longer an empty file, it now has the characters no comment in there. So, and we're going to add that to the tree again. Let's go and have another look. We now have a completely new blob. The old one, the empty one, is still there because it's been referenced by a commit. However, we've now got a new one that's completely different. This is one of the fundamental differences in Git from something like Subversion. Subversion tracks patches. You start with a file system, and then you have a bunch of changes to it. That makes it very hard to manipulate over time because you can't really replay history and modify history as you go. As anyone who's ever anyone checked in a password file and then tried to remove it from Subversion will tell you getting information out of it is very, very difficult, changing history. Git does allow that. The other one is one of the fundamental insights that Linus Torvalds had when he created Git is that file space is cheap. It's much easier to just store every variant of a file rather than try and keep it in deltas, because then you can apply new algorithms on top of that. New merge systems. Your merge systems aren't baked into the underlying data model. Now, later on, that changed, particularly when we came to networking. So we do have the ability to compress and delta optimize and so on, and we'll come to that in a bit. But fundamentally, Git always keeps a complete history of a file, or a file system or a commit around. It doesn't really deal in deltas, except in certain cases that aren't really important for thinking about Git. So that's the fundamental, that's the absolute bottom layer of Git. Let's jump one level up the stack of technologies in Git, and talk about refs and branches and tags. So you've probably heard about branches and tags. Maybe you've probably seen references to refs. Refs are basically the abstraction on top of which the branches and tags are built. So what is a ref? A ref is just a pointer to an object. That's it. There are, and that is powerful, and that's one of the reasons why things like branches and tags and so on are so fast in Git, is all they do is literally point at a hash. I mentioned that this is we using refs to create branches. So what is a branch? A branch is just a diversion from a common point in the history. So master points at one hash, feature points at a different hash that goes back through a different set of commits but has a common ancestor at some point. And you can walk back that tree, you can walk back, take both of those, master and feature, and walk back through them and find their common diverging point. And we'll be using that later when we talk about how we do a merge. Now, the other one is, I mentioned, is tags. What is a tag? Well, a tag is just a ref that doesn't change over time. At its simplest level, it just points at a particular point in the history, and that's it. Now, I am skipping this slightly. There is something called a signed tag or a tag with a commit, but that really is just you have a commit that points to an object, and a tag points at that. So really, it's the same levels of abstraction. But at the simplest level, a tag is just a ref that doesn't change over time, whereas branches actually do. So let's have a look at how that's implemented. We're going to create a branch and a tag. So the first thing I'll do is I'm going to create a tag called a tag and a branch called a branch. And then we're going to have a look at somewhere else in the tree, the git/refs subdirectory. And that contains two subdirectories, a branch subdirectory, so a heads directory, which contains all the branch tags, and a tags directory, which contains all the tags. These are really just conventions. And as you can see, I've done cat, which just spits out the contents of the file. And as you can see, it is nothing more than a file containing a hash. That's all it is. This is why branching is so fast in Git. It's almost a null operation. It's literally writing a handful of bytes to a file. That's it. So we've messed around with branches tags. We had a look at them. And one of the first things you'll do in the case of when you're starting to experiment a bit more with Git is you're going to use rebases. But we'll come to that in a bit. And you've done it. How many people have used git reset? Right. How many people screwed it up? Right, almost exactly the same. Everyone's done it. The other ones, they're all lying, by the way, the ones who didn't put their hands up. So what is a reset? Now, reset is like a bunch of things. It's a heavily overloaded command. But at its simplest level, it just moves a tag or moves a ref. It just manipulates the point in the tree that we're currently looking at. Now, there are a bunch of things like soft and hard and so on. All it does is manipulate the working directory. But at the fundamental level, all it does is move a reference along, forward or backward along the tree to some point in the past, or possibly into the future, if a future does exist, as it does now, because we've moved backwards in time. So the problem here is, if we do a reset and we reset it to something we didn't actually want to, what happens to that information that we've moved away from, we no longer have a reference to? Well, here's trick number one, and one of the most overlooked and most powerful ideas in Git for getting yourself out of trouble is something called the ref log. How many people know about the ref log? Okay, not enough. 3 or 4. What happens is when you manipulate references, Git makes an entry in a file that basically says, here's a bunch of things that I did, and here's what the reference was pointing at in the past. This means that if you do something, you do a reset, or you take any action in Git, there will be a record of it, what you did, and what the state of it was before you took that action. Very, very powerful concept, and again, we'll be using that later to get ourselves out of trouble. But that said, you would notice that I talked a bit about how Git only keeps all objects around. It keeps all copies of a file around, even though it may not be used anymore. In particular, as you saw there, we might actually create a branches, work on something, and throw it away. What happens to all those dead objects that are lying around? Well, Git has the concept of cleaning up after itself as well. It does this when you do a pull or a push, but you can also do it manually, and it will occur occasionally by itself. Git will do something called a GC, or garbage collection. You may notice how, if you know a bit about how the JVM works, the Java Virtual Machine, this looks an awful lot like the object trees of the Java Virtual Machine. This is, GC works very much the same way. What happens is, I should play that again. If you have an object that is no longer referenced, and you do a GC, it will destroy any objects that are no longer referenced. And we'll be using that later to show you that one weird trick I mentioned. So what I've done here is I've moved the reference away from the end object and then a git GC. Now normally Git will wait 2 weeks before it goes around destroying your information for you. So you have a grace period to fix things up. However, what I've done is prune all here is just basically said don't worry about that grace period just to prove the point. And it will destroy that object and clean up after itself. The other thing git GC will do is it will save some space. Now, I was almost not going to talk about this next bit, but I think it'll save some confusion later. As Git evolved, it became necessary to operate with Git trees over the network. And ultimately, Git trees, particularly something like the Linux kernel, gets very, very big. So this space did become somewhat important. So they introduced the concept of a pack file. A pack file is a compression of Git objects. And what it does a lot of compression, it does a lot of zlib compression, it does some really clever stuff involving laying out on the disks for optimal speed, and then it does delta compression. So what happens when you do a GC, all your objects will go away and be turned into pack files. Now, the pack file format is exceedingly opaque. It was undocumented for a long time. Linus Torvalds came up with it, and the main documentation is inside the Git source tree. There's a dump of an email he sent onto the Git mailing list about how it worked in his head. And that's it. It is exceedingly opaque, but it's also very fast. It is designed to be very fast on disk. Now, if you've ever worked with very simple database systems, it will look quite familiar to you as well. Database systems, particularly like Berkeley DB, have a binary and they have an index that is used to find information inside that binary blob. So in some ways, the pack file is like a random access database with fast lookup. But in many ways, this is not important. Don't worry about this too much. This is used primarily for optimization on a disk and optimization for transferring information over the network. It is not important to know much about it, and it does not change the Git's underlying model in any way, shape, or form, any more than, say, compressing a PNG changes what the image is. The underlying data model remains the same even with pack files, and they are really an implementation issue, and they may change over time, but the underlying model will not. The idea of blobs and commits and trees, etc. So that's the lowest level, and we've shown you how to create a branch. The problem is branches by themselves are not a lot of use, because at some point you want to rejoin the streams of history. You ultimately want to have a single endpoint that you are all commonly working from. Normally master, maybe it's a release branch, whatever, but ultimately you want to take your work, having worked on it on a branch, you want to move it onto some other branch, normally the mainstream of development. So this is where we're going to talk a bit about merges. And merges where things get a little bit complex, and I'm not going to go too deep into them because there's a lot of interesting implementation information that is in some ways secondary to the core idea, but I will take you through the basics of this. So what is a merge? Now, we've talked a bit about we can very fast to create a branch because all you're doing is basically just creating a new pointer that you can then create new commits off that don't necessarily match what someone else is doing. You've got a divergence, but a common point in history. Well, merges resolve that. And the interesting thing about a merge is it has two parents. A merge commit has two parents, not one. And so you can then go back, as you walk back through history, you can decide, do I walk down this branch or do I walk down this branch? And this is why when you destroy branch references, you're not actually destroying the branch itself. The branch will always remain there because the commit remains that points to two different streams of history. It's very important. Now, how merges actually work is quite complex, but it's also pluggable, which is quite interesting. The one that Git uses is something called resolve. That is it's a recursive. There's a recursive walk back through the history to find the common point, and then uses that information about the common point to resolve any discrepancies. The reason this is why merging in Git works so much better than it does in Subversion is because of this. It can find a common point in history and then replay across that and find out where things differed and resolve them intelligently. Now, there is one exception here. There's a special type of merge, and it's actually a default called a fast-forward merge. So now what we know now, we can reason about what this is. So let's replay that. If we've created a branch, and we've worked exclusively on that branch, and we go to do a merge, but no work has occurred back in master, what's the difference? Has there really been a branch at all? Now, by default, Git will do something called a fast-forward merge, because literally it is faster. All it does is just shift the head and basically pretends that the branch never occurred. Now, this can be good. Some people like to have a very clean tree with no branch histories in them. However, a lot of people do not like destroying history. So there is a flag called noFF, and what it will do is create a dummy merge for you. It creates a dummy merge commit that does nothing except contains two parents, one back to the branching point and one to the new head. Therefore, you can maintain the history of the branch. Now, whether or not you use this is largely a policy issue. There are pros and cons to both. Personally, I like to keep history around. Others like to keep a very clean tree. Others like to hide the fact that errors occurred and so on, if you're dealing with a customer and so on. I personally think honesty is the best policy most of the time, but I understand. So if you do not have a divergence, by default, Git will not create a merge commit, and you will lose the history of that branch. Whether or not you want to do that is entirely up to you. Now, there is a way of forcing that situation, and we'll talk about that in a little bit. Briefly, I just want to talk about the merge strategies again. There are a bunch of them. Resolve is the one that was traditionally used quite a lot for merging in traditional version control systems. Recursive is the one that was introduced with the Linux kernel. As I say, what it does is it goes back and finds the common ancestor point and then walks back up both trees, resolving issues as it goes. And it will actually create intermittent dummy commits and work from those. It can handle things like cross merges. You're re-merging information from the master branch into yours, and then you merge back, but the tree carries on living, and you merge again. These complex systems happen a lot in the Linux kernel, which is probably one of the biggest software projects in the world. And recursive has been shown to work very effectively in an exceedingly complex environment. So it's one you probably want. There are others, though. Octopus merge is where you merge multiple branches all at once. Maybe you've diverged into like 5, 10 different branches, and then you want to pull them all in one go. And that can actually, so you might have a commit that has maybe 8 or 10 different parents. Now, this is very specialized, and generally speaking, it will only work when you have non-overlapping changes. Once you get into a merge situation of conflict resolution there, it's going to be very, very ugly very fast. We do use it internally at Atlassian we've got our blog system uses Markdown and text, and we will actually use this because we're generally working on each on our own post and not collaborating. If we merge them all together, they won't generally touch each other because there's no shared files. And we'll use that to build a staging server. So rather than, if I'm working on a branch and Tim's working on a branch, we want all of those branches to appear on the staging server at the same time. We'll use an octopus merge to pull them all together. Ours is interesting. There's also another one called theirs, and that basically says, let's create a merge point, But let's just pretend that entire chunk of history over here doesn't exist. We're not going to actually merge the two trees. We're going to replace one with another. This generally happens when you've got like version 3 of your application and it's diverged completely from the previous history, and you want to just completely replace it. It's not common, but it is useful to know about. Subtree is quite well known. It actually will use another Git repository as a chunk of your repository and pull in changes from there. It's a little bit like Subversion's externals, but not really at all. That is probably a talk to itself, but useful to know about. You can basically reference other trees and pull them in. So if I want to statically pull in a left pad or something because I don't believe that it's going to remain around for much longer, I can basically pull that in, and there's one giant commit inside my tree is actually a reference to another tree. And also it's custom. These are pluggable. Now, if you've got some binary or proprietary file system or config file system or something that Git wouldn't know how to merge, but you might know how to merge it intelligently, you can plug in your own merge strategy. A great example would be something like XML. You've got an XML format. Theoretically, if you've made a bunch of changes and someone else made a bunch of changes, and the two files look completely different now. However, if you actually were to break that out into a DOM, and then basically recursively fix it then and then dump a new text file, then you can build your own pluggable merge system in there. But instead of merging, sometimes people do something pretty crazy. They do something called rebase. Our old friend rebase. What is a rebase? It's not a merge, although it does actually use some of the concept of merging in it. A rebase is basically where you say, I'm going to change history. I'm going to pretend this branch never occurred. I'm going to put myself in the fast-forward situation. I am going to replay history. Now, because we know now that if we go back to the history, we can see that there's a branching point there. And we know that if we actually were to move those objects up, the first commit after the branch point would now have a different hash, because it would be pointing to a different backwards commit, which would change its hash, and then would therefore change all the hashes of all of the commits up the tree. So we can't just move these in place. We need to replay history. We replay each of these one at a time on top of a different point. Each point along the way, we resolve any conflicts that occur. So it's kind of like a series of merges that occur piecemeal. This is the simplest level. Now, one of the cool things about that is if you're replaying history, you can change history. And it's one of the power of rebase. You can do things like, well, maybe that one commit that contains that password file that I really shouldn't have committed, let's remove that one commit. And then we can replay that piece of history and pretend it never happened. We can do things like, well, maybe these two commits should have been one commit. Let's squash them together while we're replaying them. And let's do other things as well. Rebase can get you into a lot of trouble, and I'll show you some of the ways it can, but the power of the replay also gives you the ability to fix the issues you're about to create. Which brings us really to the ultimate point of this talk, which is how do you get out of trouble? I'm curious, has anyone ever seen this before? This video? No one. Okay, apparently it looks like it only ever played in Australia in New South Wales. It's the original advert for Prince of Persia, Sands of Time. Makes sense now, doesn't it? So, apparently no one remembers this except me. Okay, so, who's done this? Yep. So maybe, probably like 10, 15 people here have done that. How many of you fucked it up when you did it? Yeah. The ones who aren't putting their hands up are lying again. Everyone has done it. It's a rite of passage when you go, I get Git, I know what to do, blah, blah, blah. That Dunning-Kruger effect she was talking about downstairs before. Yeah, I'm fine, I know what I'm doing here. Boom. Everyone has done this. You do a reset hard, and suddenly you've gone, oh shit, I wanted something in there. How do I get out of this? Well, I've destroyed the information. I have no way of getting it back. Or do we? Who knows how I would get that back now? Someone said, yes? Exactly. Reflog. See, this is the power of it. Because when I did the reset, I screwed up. I no longer know what that magic hash was, because who the hell remembers hashes? But reflog remembers. So I want to fix that issue. All I have to do, just going forward. So having done that, so we'll jump back get a bit further ahead here. So having looked at the reflog, we can look at what the previous state was. We look up the hash, 6CC6637. I wonder if I actually used that in the example. Yes, I did. Hooray. We do git reset hard, but now we target the previous hash, and now we are back in that state. That happens because Git does not destroy information for 2 weeks. It keeps 90 days of reflog around by default. You can change any of these defaults, by the way, just in the git config file, and it will keep the objects around, not GC them for 2 weeks. So you have a grace period. You can look at the reflog, and then you can basically jump that reference back into the previous state. The other one, this is a great one. You decide you want a clean tree, or you've got a long-running branch, you just want to pull in changes in a clean way, and you've done a rebase. Rebase has broken the build, though. You do your rebase, you run your tests afterwards, boom, it's broken. I'm going to show you 2 ways to fix that in an automated fashion. Now, you can obviously go back and screw things up. First thing you want to do is obviously, well, we know that we can get back to the previous state. We're going to look at the reflog again, and we go back and find where we were before. However, so we've used the reflog. Then we're going to use something called rebase exec. This is one of the most powerful ideas that no one seems to know about. I'm like talking to some really experienced people like Jez Humble and people like that who haven't heard of this one. What you can do is, as you are replaying that, so you do the rebase again, but after each point in the rebase, you run a command. That command could be anything, but most commonly it's going to be running your test suite. So each step along the way, you do one step of the rebase, and then you run a command. And that command, if that command fails, the rebase will stop and say, how do you want to resolve this? And then you can make some manual fixes, you can go back and start again, you can do whatever you want, try and work out what the differences were, and then you can say, well, continue. And then you can carry on from there. So this gives you the ability to interject during a rebase and fix it up as you go. Very, very powerful idea indeed. I'm also going to show you another one that isn't quite so well known. It's very commonly used in the Linux kernel community because they have huge branch merges and they find regressions months later. Now, generally speaking, you shouldn't need to do this because obviously your test suite is 100% coverage and it's going to find your issues immediately. The Linux kernel doesn't have that advantage. Generally speaking, it'll stop working on some weird hardware that like 100 people have and it's 6 months down the line and they can't just go back. So what they're using something called bisect. What bisect does, we can take a known good point. I can go back to a previous version of the Linux kernel, compile it, run on a machine. Oh, it works. I take the current version of the Linux kernel, and it's broken. Which point did it break at? Well, what you do is you tell Git, well, there's a known good point here, and there's a known bad point. What I want you to do is jump to the midpoint and build that. Now, there's 2 ways you can do it. You can do it manually, which you generally do in the Linux kernel world, where you'll jump to a certain point and say, okay, I'm choosing this one for you, please test this. And you'll compile it and you'll run it on the machine, and then you go back and say, that was good or that was bad. And at that point, if it was good, it'll move the pointer forward to the midpoint, or if it was bad, it'll move it backwards to the midpoint and then go do the whole thing again. Of course, you can also do this in an automated fashion. If you have a bunch of tests or a particular test that you can run to check the state, to find out if this particular commit was broken, do that, and Git will just do the whole thing for you. Jump back to the half point, good, bad, jump forward, good, bad, jump forward. Oh, there we go, and it will fail, and that is the one that broke the build. So very, very powerful idea. Not widely used outside the Linux kernel community, but is useful when you have some regression that's turned up at some point in the future. and you don't know where it came in. It generally works for things that aren't easy to test in an automated fashion, UI problems, so on. A broken PDF format, something like that. So that's one of the core ideas. So that's, there's lots and lots more other problems that you will find. Hopefully I've given you enough of the tools to work out how to fix these things for yourself. So for the last little bit of this talk, I'm going to show you a little cool thing. Doesn't have a huge amount of use, except when it does, and then it's very useful indeed. I'm going to give you the powers of invisibility in Git. I stole it off one of my workmates, it's great. So we're going to show you how to hide shit in Git. People do this, by the way. See, the thing is, we know that we can create objects in Git, and we know that, generally speaking, they come from a base point. But why does it only have to be one starting point? We've done that Git add, we've done the Git init and Git add, and we created a starting point. Why can't we have another object in there that's actually not related? Well, you can. You can create files or even a completely separate history inside the Git repository and jump between them. So here's how you do that. This is where we get down to the low level. This is what I'm talking about. I didn't know these commands I'm about to show you existed, but I knew they must exist because I know the Git model. We're going to create an object inside the Git repository. We're going to use hash objects. I literally didn't know what the command was, but I knew it must be out there, so I knew it had to go and Google or search through the man pages and work out what it is. The way you write a completely new object into the Git tree, this is below the level of your normal Git commands, use hash object. Hash object is a command that will take a particular file that you pass it or any information and will tell you what the hash of that would be under normal circumstances. You can add a -w and it will actually write that object into your tree. Very, very useful, not. In particular, the reason it's not going to be very useful is because in 2 weeks, it's going to get GC'd. It's just sitting there, it's got no references, there's no reason for it to be there, it's going to get destroyed. Except, of course, like the JVM, if it has a variable name, it is a real thing. So we can actually create a tag. We're going to give the tag a name of hidden. We're going to point it at the hash that we created. And obviously, if you know Unix, of course, you can just chain all these commands together, take the output of the hash and use it as the input for the tag, etc., etc. And now we have an object that's floating in the tree. Now, there's no reason why we couldn't actually then go, well, make that create a commit on top of that, and a tree on top of that. And then we can actually, later on, have a new commit that points behind it, back to it. So you can actually create a completely separate tree. You have multiple trees inside the same Git repository, if you so wished. However, we're using it now just to hide a single file, a single bit of information in there. How do we get that information out? Well, we know that we have a tag. The tag has a name. We can use that. So let's just get it. We know, well, we don't know. We don't know that there is a command called getcatfile, but we assume there must be one because, there's objects, and sometimes you're going to want to see the contents of objects, so there must be someone to spit it out. Catfile is the magic file you would use. In this case, we just point it at the reference that we created, and we can get the information out. So that's actually the old Smith family recipe for poutine. Poutine being basically Irish vodka, but it'll make you go blind. Despite my name, I'm actually of Irish background. I have a strong suspicion they were all on the run from something. Probably the poutine. Now this is an interesting little fact. Not a huge amount of use in and of itself, except it is actually used. If I go to the Git repository, the actual Git repository for Git, and I do that command, catfile Junio GPG pub. Junio, the maintainer of Git, put his GNU PG, GNU Privacy Guard, public key in there as a standalone object just floating there that you can use to do checks against the signs, the signatures on the releases. Now, that is actually a little bit redundant because if you're using the key inside the repository to check the keys in the repository, you've got a recursive security issue. So it isn't actually a huge amount of use. You should verify this via some external method. but this is actually in use inside Git itself. Another fun fact about that, totally blew up Bitbucket. So I work for Atlassian, and we have Bitbucket. Originally it was Mercurial only, and then we added Git support. And then when they were doing that, one of the first things they obviously did was import the Git repository into Bitbucket as basically their stress test. It was blowing up like crazy. It took them ages to work out why, but their algorithm wasn't taking into account of the fact that there can actually be floating objects inside Git repositories, and really screwed them up. Also, another fun use for this, by the way, is GitHub pages. I really shouldn't talk about the competitors, but I've got no quarrel with them. They're fun guys. I've got to drink with them. So GitHub pages, where you can actually have a website attached to a repository, but it's not actually part of your source code repository. That's how they do it. They actually create a separate root commit and then just work from that. So you actually switch backwards and forwards between completely separate information inside this one repository. All your metadata is about it. All your documentation is actually stored in a separate tree inside the same Git repository. So I've covered quite a lot there, and unfortunately I'm out of time. I'll be hanging around for the rest of today. So if you've got any questions, feel free to come and talk to me. Later on today, Nicola Paolucci will be turning up from Atlassian. He knows more about Git than me, so he'll be a good person to talk to as well. You'll see him hanging around. He's talking at 3:30, I think, as well. I think about Docker. He knows a lot. He's a very early advocate for Docker as well. But just to recap, that is the Git model. It's in its entirety. You have blobs that contain the information that you want. You have trees that point that information and give you metadata about those objects, primarily about their file names and so on. And those trees can be recursive. Trees can point to trees, gives you recursive directory structure, very much like a Unix file system. Commits track that information over time, and everything is held together by hashes. A change results in a new hash, results in a new point in the tree's history, and history is stored over time. You can have commits that have more than one parent. You can have they can point to each other, and they can point to trees or objects or whatever you want. But these are the fundamental building blocks, and you can actually combine them in any way you want if you know the commands. And if you don't know the commands, you know the command must exist somewhere, so it's very easy to find out what that command actually is. If you just a quick Google, you can assume that someone has tried to solve the same problem as you before. So now that we're all smart and we all know how Git works, I thoroughly recommend going off to your repository and using like cat files and manually create references and stuff like that. Don't worry, tell the boss I sent you and it'll all be fine, don't worry. Dunning-Kruger didn't know what they were talking about. So, that's the talk. Hopefully it's been of use to you, and hopefully it'll make the next step of your Git journey a little bit easier now that you can have the tools to reason about how Git works and hopefully understand it some more. So that's it.